Okay, so let's start our talk tonight with power. So power is the probability, so it's a probability, keep that in mind as you are working through things. Okay, so it is the probability that the test will reject the null hypothesis at a chosen alpha when the specified alternative value of the parameter is true. Okay, it's your probability of avoiding a type 2 error. So let's kind of talk through that again. So it's my probability that my test is going to reject the null hypothesis at my given alpha when the specified alternative value of the parameter is true. So this is a good thing. Okay? It's not an error, it's a good thing. It's my probability of avoiding a type 2 error. Because remember, a type 2 error is when I when I fail to reject my null hypothesis when I should reject it. Okay, so a type 2 error is when I fail to reject my null hypothesis, okay, when the alternative hypothesis is true. So power is my probability of avoiding a type 2 error. Basically, it's my probability of getting it right. Okay, I've rejected the null hypothesis, okay, when the alternative value is true, which is what I'm supposed to do. Okay, so we are less likely to make a type 2 error. So basically, we increase the power of a test. Okay, so we increase the power of a test, which means we decrease our likelihood of our type 2 error with a bigger sample size. So when we increase the sample size, that increases the power of our test and decreases our chances of having a type 2 error. Okay? If our alpha is larger, okay, if our alpha is larger, because this means our p-value doesn't have to be as high, so we increase the power of the test. And we also can increase the power of the test if our alternate value is far from the null hypothesis. So not if it's like if you're talking about the potato thing and it was 8% of the potatoes, more than 8% of them had blemishes. If it was, and our null hypothesis was 8%. So if our alternative value was like 75% of them, you know, the further it gets from the null hypothesis. All of these things here can increase the power of the test. So decrease our likelihood of a type 2 error. So another way of saying this is that it's our probability that we're going to find convincing evidence that the alternative hypothesis is true, given that it really is true. Okay, you won't be asked to calculate this. You could possibly be asked to estimate it from a diagram or from a simulation. So we're going to look at one of those in just a minute. Okay, what I want to look at first real quick is this right here, this power and the type 2 error. Okay, so the power of a test is 1 minus the probability of a type 2 error. That's what the beta is there, our type 2 error. So 1 minus the probability of that. So remember that power is a probability, so it's going to be a number between 0 and 1 because it's a probability. The closer it is to 0, the test has almost no chance of correctly detecting that the null hypothesis is false. So the closer it is to 0, your test is not as strong. The power of that test is not as good. Okay, because there's almost 0 chance that it's going to correctly reject the null hypothesis when it should, when the null hypothesis is false. The closer it is to 1, okay, the closer your power, your probability is to 1, then the test is very likely to reject the null hypothesis in favor of the alternative when the null hypothesis is false. So it's more likely to get it right, okay, and less likely to make a type 2 error. Okay, so let's look at what we have going on here. So this is our potato chip example again. So the potato chip producer wonders whether the significance test of the null hypothesis where p equals 0.08 versus the alternative hypothesis where p is greater than 0.08, based on a random sample of 500 potatoes, has enough power to detect a shipment with, say, 11% blemished potatoes. So is the test good enough to detect that? In this case, a particular type 2 error is to fail to reject that null hypothesis when the actual value is 0.11. So failing to reject that null hypothesis when they really should. Okay, so the figure that we have over here on the side with the diagrams there and the bell curves shows two sampling distributions of p hat of the sample. Okay, one when p is 0.08 and another one when p is equal to 0.11. So we've rejected the null hypothesis if our sample yielded a value to the right of the green line at the sample equals 0.1. So based off of our significance level of alpha, right here is our cutoff. That's where we would reject the shipment. So then if you look at the sampling distribution on the bottom here for 0.11, the shaded area to the right of the green line represents the probability of correctly rejecting the null hypothesis when p is equal to 0.11. So right there. So the power of the test, okay, to detect p equals 0.11 is about 0.76. So in other words, the potato chip producer has about a 3 in 4 chance of rejecting the truckload of potatoes with 11% blemished potatoes based on a random sample of 500 potatoes from the shipment. We would fail to reject the null hypothesis if the sample proportion falls to the left of the green line. The white area under the bottom normal distribution shows my probability of failing to reject the null hypothesis. So failing to reject to the left, rejecting it to the right. This is the probability of my type 2 error. So the potato chip producer has about a 1 in 4 chance of failing to send away a shipment with 11% blemished potatoes. Okay, so if you look at, so you can see that here in these diagrams, right, with our probabilities. Okay, and so these are our probabilities of our type 1 and our type 2 error. So you will not be asked to calculate the probabilities of these errors, but you may need to be able to look at something like this to determine them. Okay, so let's talk about our conditions for performing a significance test about a mean. Okay, this is the same as we did before when we did confidence intervals. A lot of this stuff is the same. And again, we're performing basically the same thing that we did when we were doing significance tests about a proportion. We're just changing a few things. So we're going to try to be very quick about this. So our conditions are still pretty much, they're still the same. For a mean, right, we need it to be random. We need our 10% conditions met. And remember, for a mean, we need normal to large sample. For a proportion, it is the large counts is the one for the proportion, where normal or large sample is the one for mean, right? Our normal or large sample is that our sample size is greater than 30. If we don't know the population distribution, if it's less than 30, then we've got to use a graph. Do not use t-procedures if I have a strong skew or outliers. Okay, so let's look at our example for this. Okay, so let's look at what we have here with these with the batteries that we looked at before. So we've got 3 graphs down here. Our problem here is to check the conditions for carrying out a significance test of the company's claim about the deluxe batteries. So the first thing that we need to do is check for random. Okay, so for random, we had an SRS of 15 batteries, so we're good to go on there. Okay, for 10%, Okay, we've got 10 times my sample was 15, so 150. So we can assume that they make at least 150 new AAA batteries. So we can assume that that one is met. And since this is a mean, our last one is normal or large sample, not large counts. Normal or large sample. So for this, we're looking to see if n is greater than or equal to 30. Well, our sample is 15, so it is not. So this one is not met, which then means I need to move on to graphs because I don't know the population distribution of I don't know the distribution of my entire population. So looking at all three of those graphs, there is no strong skew. There is some skew. You can definitely see some right skew here in the box plot, but there is no strong skew. There are no outliers, so I can assume that I can do normal calculations on this. Remember, if I saw any skew or any strong skew or outliers, I wouldn't be able to do it. Also, remember, you can generate these on the calculator. That's okay if you generate these graphs on the calculator, but you must draw one of them. Okay, you must draw at least one of them. You don't need to draw all three of them, but you do need to sketch out at least one of them on your test. Okay, so the same as we did with the proportion, as we move further into our test, we're going to need to calculate our test statistic. Remember, you need to show this test statistic. You can do all of this work on your calculator, including you could calculate an interval on your calculator and do all of that, but you have got to show the test statistic. Remember, that's our standardization of the data. It's showing how far my sample diverges from the parameter specified by the null hypothesis. Okay, so in this particular instance, my test statistic is going to be my mean of my sample minus the mean of my population over the, remember I don't usually know the standard deviation of the population, so the standard deviation of the population divided by the square root of the sample size. So that'll give me my test statistic. I can also put that into my calculator. I can do the inverse t and put that into my calculator. So let's go back to that, back to the battery example. Okay, and so we have calculated our test statistic here. Okay, and so once I have that test statistic, I can use that to find my p-value. Right? Remember, I need to use on my t, I need to use my degrees of freedom, which in this case would be 14, because I had a sample of 15. So 15 minus 1. I can sketch out the curve for this. We've got 0. Right, and this would be labeled, this time this would be labeled as a T. I'm trying to use a stylus to make it less messy, but I don't think that's working. This would be labeled as a T distribution with degrees of freedom equals 14. You need to be sure to specify that. Okay, and so what you would be looking for here, my test statistic would be about here. Right, and so I'm looking for the probability that t is greater than or equal to 1.54. Okay, and so this is for a null hypothesis of 30 and an alternative hypothesis of greater than 30. So my p-value, again, remember, it's your probability of getting a result, in this case, this large or larger. Okay, so in the extreme, in the direction of the alternative hypothesis, which is greater than. So it's my probability of getting a result this large or larger in the direction that's indicated. So that's the larger, larger. Otherwise, it would be smaller, smaller. Right? And so I can plug this into my calculator. I can use that TCDF. Right? TCDF. And with my lower, okay, being 1.54, my upper being a big giant number. Whoa. and then putting in my degrees of freedom at 14. Okay, and that's going to give me my p-value of 0.0729. Remember, if I use my technology, that's fine, but identify your lower, upper degrees of freedom. Identify everything there. Okay, if this was a two-sided test, I would just take this p-value that I have right here and I would multiply it by 2. Okay, and so I would be able to figure out the p-value of my of a two-sided test. So this right here, this p-value in context here would be the probability of my getting a result of a mean battery life of greater than 30 hours, okay, would be 0.0729. Okay, so let's go all the way through an example here. So we're performing a significance test regarding the mean. Okay, so in the problem here, we've got a level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. There's your results. Okay, and then your dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So the problem part A is, do we have convincing evidence at the alpha 0.05 significance level that aquatic life in the stream is at risk? And then part B is giving a conclusion, and we'll get to part B later. Let's just do part A first. Okay, so I'm performing a significance test. So same as I did with a confidence interval, with a significance test about proportion, I need to do my 4 steps. We are always doing those 4 steps, mainly because on our AP test, these rubrics all have 4 points to them, and hey, guess where they come from? Your 4 steps. Okay, so the first step, right, is our statement, or our stating. One of the things I noticed on some of your mini labs and some of your work is that we're not being as specific as we need to be. Remember that, for example, if you took sample data from people only during third lunch, then you can't say that this is the mean for everybody at West Mesquite. It's only for people that have third lunch on B days. Okay, so just keep that in mind when you're doing your statement. Be very clear and very specific with your context. So for our statement for this, we want to test the claim. So we want to test the claim that about the true mean. Remember that word true. We've got to have that word true in there. Okay, about the true mean level, and here's my context, of dissolved oxygen, which is represented by mu, in this stream. So I can only do this for this stream, not for anywhere else. Okay, and I have an alpha at 0.05. So I've got my true mean level of dissolved oxygen represented by mu in this stream at an alpha level of 0.05. And then I'm going to state my hypotheses here too, the things that I know. So in this case, my null hypothesis is, oops, remember, don't do that. I got to break that habit. My null hypothesis is equal to a mean of 5, because that's kind of my demarcation of where it's good and not okay. Okay, and then my alternative hypothesis then would be anything less than 5, because that's not okay for the aquatic life. So as I move into step 2, I need to go into my planning stage. Let's get rid of all this stuff. Okay. So for step 2 is the planning. One of the things we need to keep in mind is we need to say what we're going to do. Okay, so I'm going to do a 1 sample t-test for mean if the conditions are met. We're leaving this step off sometimes. Okay, we're leaving off the fact that we're doing this 1 sample t-test if our conditions are met. So make sure that you're stating which test it is that you're going to use. And then you need to go ahead and check your conditions. Okay, so I need to check my randomness. Okay, it was random locations along the river. So that one is okay, along the stream. Okay, my 10% condition Okay, I took 15 samples I took samples from 15 different locations, and I can assume that there are more than 150 locations. I could take samples for every 2 inches working my way down the river. Okay, so there are more than 150 spots that I could take samples from. And then because this is a mean, my last condition, right, is my normal or large sample, not large counts, because large counts is for proportion. So my normal or large sample, I don't know the distribution of the population, and I only took 15 samples. So 15 is less than 30. So then I need to check my graphs. Okay, so when I check my graphs, of course those are going to go behind. So when I check my graphs here and I look at these, I don't see any strong skew anywhere. I don't see any outliers, so I can go ahead and assume normal calculations here, and I can check that one off. And remember, I would want to sketch one of these. If I did all 3 of these on my calculator real quick, I would want to sketch one out on my AP test to make sure I'm getting full credit. So from that planning stage, we need to go to the do part. We need to go ahead and run our calculations. So let's clear this stuff out of here. So in the do, I'm going to go ahead and, I know you guys are fans of the calculator, so I'm going to go ahead and use the technology here. So in this case, my lower is going to be, because I'm looking for less than, so I'm going to go way down to negative 10,000, and upper of 5, and a degree of freedom of 14, which is going to give me 0.1816. Okay, so this is my p-value, but I would not get full credit on my AP test here because I have not listed out my test statistic. So I need to be sure that I put my test statistic in there, which is going to be my mean of this data up here. So my mean there minus my parameter, and then over my standard deviation of the sample over the square root of the amount of the number of samples. That should be square root of 15, okay, which gives me negative 0.94. This would be okay, but I cannot just do this part here. I cannot just do this part here and expect full credit because I did not show that test statistic. You must show that test statistic. Okay, and then we need to move into part 4. And part 4 is our conclusion step, or our conclude step, right? That interpretation. So conclude. So I'm going to conclude that because the p-value, and I'm going to state what that is. So because the p-value 0.1816 is greater than my alpha equals 0.05, okay, we will fail to reject the null hypothesis. And then I need to put my context. So I did, and if you guys, I know a lot of you are looking for kind of your blanket statement. Here you go. Because the p-value, whatever it is greater than or less than your alpha equals, you fail to reject or you reject. Okay, and then you put in your context. Okay, we do not, in this case, we do not have, so either we do not have or we do have convincing evidence. Okay, so we do not have convincing evidence that the mean dissolved oxygen level in this particular stream, is less than 5 milligrams per liter. And so there's all of my context. I know your context is a lot, but you got to put it all there. All right, so now let's move on to part B. So part B is, given my conclusion in part A, okay, a type 1 or a type 2 error, which kind of mistake could I have made, a type 1 or type 2 error, and explain what that would mean in this particular context. Okay, so what I could have done here is, so based on my conclusion is that in my conclusion, I failed to reject the null hypothesis. Okay, so the type of error that I could have made is a type 2 error where I failed to reject the null hypothesis when I really should have rejected it. And if you did that, that would mean that the mean level of dissolved oxygen really is less than 5 milligrams per liter, but we didn't find convincing evidence for it. And so we make the mistake of saying that the stream is okay and the stream is healthy, but it's really not okay for the aquatic life that is there. Okay, so let's look at an example here of a two-sided test. And so with this two-sided test, this time we were given descriptive statistics. Okay, so we need to be sure that we're using the right pieces of information from these stats that we were given. Okay, so let's look at part A. Does this data give convincing evidence that the mean weight of pineapples produced in the field has changed this year? So let's go ahead and go through our 4-step process here. Okay, so the first step is going to be our statement. Okay, we want to perform a test, right? So we want to perform a test of to see if the mean weight in ounces of all the pineapples grown in this field, okay, is not equal to, if we want to see if it's equal or not to 31. So you could write that as, we want to perform a test of, and you can go ahead and state your hypotheses because you need to do that in this part anyways, of a mean of 31, or my alternative hypothesis, which is a mean that it does not equal 31, which makes it a two-sided test because we can go in either direction, right? Where mu is equal to the mean weight, and I'm just going to keep going, in ounces of all pineapples grown in the field this year. Okay, and we're going to make sure that we indicate that we're using an alpha of 0.05 because none was given to us, and so that's kind of our most common, and we'll go with that. Okay, so then we're going to move on to step 2. And so in step 2, there we go, now my picture is back. So in step 2, we have the planning, right? So I'm going to perform a 1 sample t-test because it's for a mean if conditions are met. So I need to check my conditions, right? I need to check if it's random. So I took a random sample. I need to check my 10%, right? And so I took a sample of 50 pineapples. We can assume that they're growing more than 500 pineapples. And then I need to check my normal large sample condition. So when I'm checking my normal large sample condition, this time I have a sample that is greater than or equal to 30. So I am okay to use to go ahead and use my T procedure on this. I don't have to check my graphs just to do it. Okay, so now we're going to move into step 3. We're going to move into the doing part. So for step 3, I can go ahead and use the statistics that were given to us, the descriptive statistics that were given to us. Okay, and so from the Minitab output, I've got a mean of 31.935 ounces. There's my mean right there. Okay, I have a standard error here of 2.394 ounces. Okay, so I am going to use the standard deviation. It gave me the standard deviation for this particular sample. So I'm going to use that standard deviation for this particular sample. Sorry, I said standard error. So I'm using the standard deviation for that particular sample. I've got to show my test statistic, right? So I've got to show my test statistic, which is going to be 31.935 minus 31. okay, over 2.394 over the square root of 50, which gives me 2.762. Okay, and then I could either use table B or I can use technology. I'd say for this, technology really is going to be much better, especially because table B doesn't go all the way up to a sample of 50. Right, so I'm going to go ahead and I can use my technology. So my TCDF, right, is going to give me, I'm going to have to multiply that out, right? I can go whichever direction I want to. So let's say I'm going to do a lower of 2.762, an upper of 10,000, degrees of freedom of 49. Okay, and then I'm going to need to take this answer that I get here, and I'm going to need to multiply it by 2 because I have a two-sided test. Okay, and so that is going to give me a p-value of 0.0081. So now I move into my conclusion. Okay, so let's get rid of this step 3, and let's do our conclude part. So our conclusion here, our conclude part, is going to be, again, because the p-value, and I will go ahead and state that, of 0.0081, is, this time it's less than my alpha of 0.05. So because my p-value is less than my alpha, we reject the null hypothesis. Okay, we have, and this time we have convincing evidence. We have convincing evidence that the mean weight of the pineapples grown in this particular year is not 31 ounces. Okay, we don't want to say higher or lower or anything, just we have convincing evidence that the mean weight of pineapples, and we need to specify that it is this year, is not 31 ounces. So when we move on to Part B asks, can we conclude that the different irrigation system caused a change in the mean weight of the pineapples that were produced? And explain my answer. So when I'm going through with Part B, I would say that your answer here is going to be no. Okay, we cannot say that the different irrigation system is what caused it. Okay, this isn't a comparative experiment, so I cannot infer causation. Okay, there could be plenty of other things other than the irrigation system that could have caused it. There could have been different weather patterns this year. The seeds came from a different place. There could have been a variety of things. There could have been more sun exposure this year, and it wasn't as cloudy as it was the year before. Okay, so I cannot infer causation just based on the different irrigation system. Okay, and we're not going to calculate the confidence interval here. It's given to us, but I do just want to go back and look at this and kind of remind you. This is the same as it was for the significance test for the Z, for the proportion. That if the confidence interval is going to give us more information. Okay, so in this mini-tab output here, I've got my confidence interval given to me right there. Okay, and so I have a confidence interval. And so I've got a 95% confidence interval. So the same as my alpha was for my significance test. Remember, my alpha was at 0.05 in my significance test. Okay, and so I've calculated that interval, and you're 95% confident that the true mean is captured there in that interval. And so it gives me, for a two-sided test here, this is going to give me a little bit more information. Okay, 31 is not included in this interval. Okay, it's really close, but 31 is not included in this interval. So it would make sense, okay, what we got from the significance test. And this basically narrows our focus a little bit more and gives us more information as to what actual plausible values would be if I'm rejecting that null hypothesis of 31. So be prepared to be able to calculate confidence intervals for t as well. Okay, we've got a little bit left in the chapter, but we're going to go ahead and stop here, and we'll just wrap that up with a short little video for next time.